seem like there was much of a break. There's actually a several-day break between this and the last lecture about distributed loads because the mathematical license went down. What I wanted to do was talk about more general distributed loads problems. We talked about simplification of how to figure out a distributed load for a trapezoidal type of distribution, breaking this up into a linear or uniform distribution and also linear distribution, right? And being able to get the equivalent point force and implication. And those add up together and give you basically those on the actual break this up. Now, what about arbitrary forces? Well, we've already talked about this. It's just the integration. We've already talked about this. So imagine you have the following type of problem. It really doesn't matter the support condition. We're just talking about getting effective. Imagine at this end, we have a load that comes about with a sinusoidal type of response. So if you allow this to continue on, it's a sinusoid. And its peak value is, let's say it's 100 pounds, and this distance here, the half side is 10 inches. Alright, how do we figure out the effective force and its location for such a distributed load? And we already know how to do this, right? The force is simply integral of distributed load function, and then the location of that force is just first, the central, right? The first moment, force times the moment on x, integrated over the actual force. Okay? Okay. The difficulty thing in this problem is not knowing what W is explicitly, and the integral is kind of a pain in the neck. So what I want to do is two things to show that, in real life, although sometimes for exams and homework problems we try to make things a little simpler for you, and we distill out some of the calculus. In real life, you shouldn't be afraid of doing integrations to actually solve problems practically. Unlike when I was a student, when we had to use slate and stuff, you've got a lot of wonderful tools that you use now, and I'm going to show mathematics, which I think is actually a great thing to learn. You don't explicitly have to use it for this class, but it helps a lot. I actually use it a lot to solve some of these solutions because I'm not so great at algebra. I make a lot of careless mistakes, and it helps me make careless mistakes. And also, it's very powerful. It allows you to do things like solve integrals, differential equations, without any effort. So instead of focusing on the details of doing the integration, focus more on the actual engineering solving it. Okay, so in this case, the first thing we need to do is come up with that function. Well, we know it looks a little like a cosine, right? So it's some sort of cosine type. Now its peak value is 100, so that gives me 100 pounds times some type of cosine. And this is going to be Wx, and this is going to be valid x from 0 to 10 inches, right? So this is the x direction, but this is x is 0 inches. 0 doesn't mean units, but okay, so it's going to be something times x. Well, in this case, a full period, 2 pi, would be 20 inches, right? So we want to scale when x equals 10 inches, we pretty much want this to be pi. So let's put pi times x over 10. All right? And that, we can check that, right? So if we put in x equals 10, 10 cancel out, and gives me pi, so it goes to 0. Okay? So that's the function. Now, to get the force, we have to integrate from 0 inches to 10 inches this 100 cosine pi x on 10 dx. And to get the location from this point, x bar, it's going to be integral of 100 cosine pi x on 10 times x dx, 0 to 10 inches, divided by f, which we find in 3 as well. So, I'm not trying to do calculus, but I'm, again, real bad at the algebra of forming the actual integration, the antiderivatives. So, and I students always like to make fun of us for making mistakes, so I don't like to make mistakes. So I use Mathematica. So here you go. Most of the computers on campus have Mathematica. It's great for doing this sort of stuff. It's what's called a symbolic manipulator. It allows you to do things symbolically. It also does numerics. But if you want to do real hardcore numerics, you have a programming language or maybe something like that. But it's real good for doing homework type of problems. So the way it basically works is you get these notebooks, and here's just a little palette with these entering things really easy. And to enter stuff in, it's really simple. Just if you want to do 2 plus 2, you just do 2 plus 2, and then to do the evaluation, you hit shift and then return. It gives you the answer. Okay? Not only can you do that, you can define variables. Do stuff like Bob equals 5. And I hit an enter, so it's not evaluated, but just doing a return. Too bad you can't see my keyboard. Show the camera coming down. Jane equals 2. Say I should make Jane equaling Bob. That's sexist. And then we can do Bob plus Jane, and the value is set. You know what I mean? And you can assign and do things very similar to a problem. Okay? You can see each one of these little things is like a block. Here's the input, the output. You can right click and just delete them. You can also put in text. So let's do an example of a distributed evaluation. And to make it a text, I kind of right click on this thing and say convert to traditional. I always actually I do it by shortcuts now. I can't protect it. Style to text. See, it makes it text. You won't evaluate it, but it's just a note for the comments. All right. So let's first write W, the weighting function. W is going to be assigned to the function. And it's just going to be 100 times cosine. Now the cosine, most functions in MATLAB start with a capital C. I think they all do. Cosine, so use capital C for cosine. We're going to help you find out what it is. And then the function brackets, to denote that something's in a function, it actually uses square brackets, like that, not round brackets, square brackets. And then it's going to be pi, so you can actually use a shortcut to get pi. You can actually pick pi off. So it's like put pi, put it in there. It'll evaluate to the 3.145. You can actually do this sort of thing. Go fancy, put over 10. Whoops, x, and then evaluated, and there's the evaluation, 100 cosine pi x on 10. Now to perform the integral, let's say f equals integral. I usually pick the little integral sign off on the right, so expression in here. The expression is W. Whoops, well, that's the lower limit. So 0 to 10. You have to kind of keep track of units yourself. It doesn't really, it can do units, but it's really hard. The expression is W dx. Evaluate it, and it gives me 0. What's cosine? Cosine is from 4. It should be. Oh. Sorry. I did it wrong. This is pi on 2. This point here should be pi on 2. So in fact, it should be pi on 2 times 10. In other words, pi on 20. So again, if I put 10 in here for x, this gives me pi on 2, which is that point. Okay? Sorry. So let's go back and change this. I can change this. This is always nice to do, is you can make a mistake like that. It's not too hard to go back and change. Now when I do this, I get an answer. Okay? Now, you can see the answer is not a decimal. It does it, it kind of tries to keep things in a rational form. And since we have integers here, albeit they're big integers, it keeps it in a rational form. You can get the evaluation of that. Use this n function. And that'll give you the value of 2,000 over pi, which is 636.62. Another way you can do it is you can put decimals after the 100 force. Okay, so that's the force. And then if we wanted to get the location, x bar, that's going to be this integral times x. So I can just cut and paste the integral, multiply it by x, get a little space there. So then divide this whole thing by f. That would be that. And that's the answer there. And we can also get the numerical evaluation of that. So its answer is, for this problem, so it stays on the screen. So the actual force itself, from mathematics, F is going to be equal to the 2,000 over pi, which is equal to 63. What was we get? 63, 636, 637 pounds. And it acts in here, the distance of xb, so it's 2.63 inches. And this. Okay? So it's actually pretty powerful. So you can do a lot of things like that. You can use it in other classes, especially with lots of calculus or solve system equations. Okay? All right, that's all I wanted to do with that.